from this portion, that away, so on and so forth. Can you guys see that? So on and so forth. So a wire can be thought of as many different point charges making a straight line. Now what the calculus class they did was they actually had to do this full derivation. So the electric field of a wire is the sum of the electric field contribution from the points charge. Now the calc-based class, they actually did this entire summation, but for you guys, I'm just going to give you guys the solution. This is K on 2 times K times lambda over R. Where lambda is the charge density. Charge density. And it is given by Q over L. So how much total charge it has divided by the total length. Or how much charge it has per unit length. So how closely situated or how compact the charges are. So this is the electric field if you were to have a wire. Yeah.
So what would be the value of R then? Because there are multiple points.
So the R would be the shortest distance in between. So this will be R.
Alright, thank you.
Yeah, that will be R. For the direction, it is radially away, or radially toward or away, depending on if it's positive or negative, from the wire. It's toward if the wire is negatively charged, it is away if it is positively charged. So wire is a continuous line of point charges.
What do you mean by radially?
That's what I mean by radially. It's not like this away. It is perpendicularly away from the wire, or towards the wire.
Oh, I see. Okay.
So from a top-down view, so from the side view, it is perfectly horizontal. From a top-down view, the electric field is all pointing away. From top down. Does that make sense? That's what it means radial. From the side view, the electric field is perfectly horizontal. From a top-down view, it is radially away.
Okay, thank you.
Towards it. So that takes care of this, the electric field from a wire. But what about a plane? To get the electric field contribution from a plane, which is the two-dimensional object, we actually use the wire as kind of a stepping stone. However, we don't use the wire in its raw form. We take the wire, and then we want to turn it, into a ring. So we grab the end, and then we form a ring around it. So let's use kind of an angled point of view. So we take the wire and we forge a ring. The reason why we want to form a ring is because this is how we get to a plane. So a plane, let's say it's a circular plane that looks like this. We can go from a wire to the plane, by taking a stepping stone for a ring, because the plane, so this is the plane, is essentially you add up a small ring to a larger ring to a slightly larger ring to a slightly larger ring, so on and so forth. Does that make sense? So plus a slightly smaller ring, plus a slightly smaller ring, plus a slightly smaller ring, and what do you get? Well, then this is how you get to a plane. Hopefully everyone's able to see this. You just add this, add that, and then it just becomes a solid surface. For an infinite plane, the electric field is the following. Eta over 2 epsilon naught. Eta over 2 epsilon naught.
What is the infinite part?
Huh?
Or the E in, is that infinite?
This one?
Yes.
Yeah, that's infinite plane.
Or what is that referring?
Infinitely large plane. So the radius is infinity.
Oh, okay. Alright, thank
So you
you.
just have so this one was a infinitely long wire. So we'll say E of a infinite wire. So it's just, super duper long. For this is a super wide plane.
Okay.
So in its limits.
Alright, thank you.
Now let's make a few comments regarding the expressions that I just provided to you guys. The electric field of the infinitely long wire, compare this to a point charge. One of the primary differences that you're going to see is a point charge has what kind of distance dependency? Look at the equation. A point charge has a r squared dependency. So the further you get, you got to square that distance, and that's how much the effect is reduced. Whereas for a wire, look at the distance dependency. It is no longer squared, it is merely decreasing in a linear fashion. What about for an infinite plane? What about for an infinite plane? What kind of distance dependency does it have? Oh wait, I forgot to give you what eta is. Maybe that's one. Eta is Q over A. So this is what's called the surface charge density. So how densely packed the charge is over, or how densely it's distributed over a certain area. And so this eta does not have any distance dependency whatsoever. So here we see that for the infinite plane is directly proportional to eta. Secondarily, we see that the distance is missing. It has absolutely no distance dependency. So here the field strength is not dependent on distance. Therefore, is the same at all points. Now this should be extremely counterintuitive. For probably the past 2 weeks, I've been trying to harp on you guys this idea of an electricity or like electric interactions occur over a distance. It is a long range effect and it is distance dependent. The further you go out, the weaker it gets. However, for an infinite plane, the further you go out, nothing happens. So this should be intellectually very satisfying or just intellectually confusing, because this is a huge conundrum. How can something, as you go further away, still maintain the intensity? How can this electric interaction not decrease? So this should lead us to ask this question of how? Why does it not decrease? With distance. Why does it not decrease with